So now that we've learned a bit about product quotient and chain rule, now we're going to take a little time to combine the rules. We can expand our horizons when we talk about which functions we can take derivatives of. This first one is a case in point. So you notice that on the surface, this is a product. We have this part and we have this part. And now that we've seen the chain rule, we can actually take the derivative of each piece. And remember, the product rule says put each piece together. So the derivative of this function is going to be something times something plus something times something. I know, it's very, very profound. So the derivative of x to the third is 3x squared. So that means as my product rule progresses here, that means it's the derivative of the first times the second, which I'm actually going to go ahead and write down actually, plus the first times the derivative of the second. Well, okay, so that's the piece we need to figure out. So we have x squared plus 1 raised to the fourth power. So it's like a u to the fourth. So the derivative of that is going to be 4 times the thing cubed, and then times the derivative of the thing. So I'm just going to go ahead and plop that right into this spot right here. So I'm going to have 4 times x squared plus 1 to the third times 2x. And then in the next step, we'll clean things up. So that means this is 3x squared times x squared plus 1 to the fourth plus, now, let's look at all the things that are outside the parentheses. We have an x to the third, we have a 4, and we have a 2x. So I'm going to multiply all of those together because we can. What better reason to do something than because we can? So 4 times 2x is 8x, times x to the third is 8x to the fourth, and that's times x squared plus 1 to the third. And as far as that example goes, this is okay as a final answer. But we can go further, because thinking ahead to the future, we're going to be having to set these things equal to 0, and one of our favorite ways to set things equal to 0 is to have factored form, as you might recall from algebra. So I'm actually going to go ahead and I'm going to identify common factors. Now, looking at each term, I notice that I have a 3 and an 8, which means no, I can't factor anything out of that. I have an x squared and an x to the fourth, which means I can factor out an x squared. And looking at the x squared plus 1 to the powers, I have a fourth power and I have a third power, which means I can factor out x squared plus 1 to the third power. Now, where does that leave us when we're factoring that out? So we're going to write the bracket here, get rid of that straight mark. So I'm factoring out x squared times x squared plus 1 to the third. So that leaves me with a 3. And since I'm factoring out something to the third from something to the fourth, that's going to leave me with the something to the first. Plus, now I'm factoring out an x squared, which means I'm not doing anything with that 8. I'm factoring out an x squared from x to the fourth, so that's x squared. And then I'm factoring out the whole shebang with the x squared plus 1 to the third. So that's really times 1, which means that's done. And we're now going to have x squared plus 1 to the third. And then if we multiply and simplify inside the parentheses or the brackets here, we have, whoops, I'm just going to combine the whole thing, 11x squared plus 3. And like I said, that's an okay answer too. I'm okay with this one for now. Chances are the derivatives we're going to take, we're not going to get anything this complicated later on, but you never know. But this is just a way of re-expressing the answer in completely factored form. So this just looks nice and more compact. Up to you. Okay, so now moving into this one. So now we have a quotient rule. Similar ideas apply here. So remember how the quotient rule works on the surface. We need the derivative of the numerator, and we need the derivative of the denominator. Now, I'm going to find the derivative of the denominator right away. So we have something squared, which means the derivative is 2 times the something times the derivative of the something. And you know, while I'm here, I'm actually going to simplify this. I'm going to write that as 4x times x squared plus 1. And that's going to make it easier for us to plop this into the derivative formula. So the derivative of the quotient is the derivative of the numerator times the original denominator minus the numerator times the derivative of the denominator all over the denominator, the original denominator. So that was the original denominator, right? And now we're squaring that, okay? Now, business as usual. Now, I'm looking at the numerator, and I notice that I can actually pull out a common factor. So I'm going to do that. I'm going to factor out well, let's see. I got a 6 in both, and I have an x squared plus 1 factor that I can take out. So I'm going to pull out a 6 times an x squared plus 1. Now, what does that leave me? Well, I'm removing the 6, so the 6 is no longer there. I have a square, and I'm pulling out 1, which means I'm going to be left with x squared plus 1 minus. Now, I'm taking out the 6. I'm leaving the x and the 4x, and I'm factoring out the x squared plus 1. So there goes that. And now, if I'm squaring a square, that's really x squared plus 1 to the 4th. So now this is going to be 6 times x squared plus 1. Now, what's in the brackets? Well, we have x squared plus 1 minus 4x squared. So that's 1 minus 3x squared all over x squared plus 1 to the 4th. And funny thing is, I do have a common factor between the numerator and denominator. I have a first power over a fourth power, which means essentially, switch colors here, this is going to go away, and this is going to become a third power. So that means the final answer is 6 times 1 minus 3x squared all over x squared plus 1 to the third. So it seems with the quotient rule, something's always going to be able to be crossed out. Okay, so that might be something to look out for as you practice these. And again, I'm going to try not to get more complicated than those. One last one, we have a product of powers, so this one's going to be really interesting. Looking at the surface, we have the derivative of a product. So that means we have this guy times this guy. So the derivative of the first is, 5 times x plus 1 to the 4th times the derivative of the inside, which is 1. Okay, so that's really just going to be, I'm going to erase the 1. 5 times x plus 1 to the 4th. The second one over here is 4 times the thing to the third times the derivative of thing. And then I'm actually going to pull that together and write that as 8 times 2x plus 3 to the third. So that means the derivative of our product is the derivative of the first times the original second plus the first times the derivative of the second. And now that might look okay to you, and honestly, that would probably be okay in most circumstances. Again, thinking about the future, factoring. So notice we have a factor of x plus 1 to a power in both terms, and we have a factor of 2x plus 3 to a power in both terms. So I'm going to go ahead and factor out the lower power. That's what we're used to from algebra. So this is going to be equal to x plus 1 to the 4th, because that's the lower power between those. And I'm going to factor out a power of 2x plus 3. That's between a fourth and a third, so I'm going to factor out the third. And now what's left inside when we do that? So looking at the first term, this one right here. So I didn't touch the 5. I took out all of the x plus 1s, and I'm left with a 2x plus 3. Plus, got to carry this plus down here. Now, I'm taking out an x plus 1. I'm leaving behind an x plus 1 and that 8. And I'm removing the whole 2x plus 3 to the third power. So we're actually almost there. So this is equal to x plus 1 to the 4th, 2x plus 3 to the third. And then to simplify inside the brackets, this looks like 10x plus 15 plus 8x plus 8, which turns out to be x plus 1 to the 4th, 2x plus 3 to the third, and 18x plus 23. And again, that factored form will be handy if we have to set it equal to 0, because now we can easily see which values of x make this equal to 0. but we're not there yet. We're just practicing taking the derivatives to be able to get there later. So hopefully this helps. As you can see, when we combine rules, more simplification can happen. So it's really going to depend on how, if it were me, I'm pretty big on simplification if it's obvious, but I'm not too crazy with it. But some, it's very important just to get set up for setting them equal to 0. So I'm not calling your instructors crazy there. So thanks again for watching, and watch out for more videos.